Okay, welcome to the notes, aka hello. Yeah, hello. In this video, let's go ahead and find the limit as x approaches -2 of the function f of x, where f of x is equal to 3x plus 2 all over 2x plus 4. Okay, here's the thing. This is just a rational function, just a standard rational function. Notice that, though, for a rational function, that in order to be part of the domain of the function, the denominator cannot equal 0. So in this situation, if we take that denominator, 2x plus 4, set it equal to 0 and solve, subtract 4, and divide by 2, we get x equals -2. But that's what we want x to approach the value of. So we can't even find f of -2 because it's an undefined value because we are dividing by 0. But there's nothing wrong with that, as long as we realize that we're trying to approach x equaling -2 from both the left, from the left and the right at the same time. Okay, so to do that, we need to find values to the left of -2 and values to the right of -2. And just a reminder, on the number line, with -2 in the middle, -1 would be over here, and -3 would be over here. So when we're to the left of -2, that means that the number we might want to use would be, let's say, -2.1. That'd be something, say, about right there. And then 2.01, so -2.01, and then -2.001. And that's helping us approach the number of -2 from the left-hand side. Now let's do that from the right-hand side. Let's say -1.9, -1.99, so say there, and then there, and then there, and -1.999. Awesome. Let's go ahead and go to the calculator so that we can actually type these in. I'll see you there. Okay, welcome to the calculator. Let's go to y equals, clear anything in here, and then let's type in the rational function. So alpha y equals, enter. Then we have 3x plus 2, right arrow, and then 2x plus 4. Now, here's the thing. This is a little bit different from what we've seen before. If we type in -2, in the numerator, we get 3 times -2 is -6, -6 plus 2 is -4. In the denominator, we get 0, so this gives us -4 over 0, which is different from 0 over 0. Yes, they're both undefined, but with -4 over 0, that's different because it's not 0 over 0. 0 over 0 is actually a value that we can make to be pretty much anything we want it to be. -4 over 0, however, is just undefined. So I do want to show you the graph here. So if we do the graph, notice that at x equals -2 here, we have a vertical asymptote. That's different from what we saw earlier with previous rational functions, because we had a factor in both the numerator and the denominator that cancels, and when you have a factor that cancels, that gives you a hole in the graph, like you saw earlier. Here, however, it's just a vertical asymptote. Okay. So with that in mind, let's quit to the home screen, vars right1, enter, enter, and ask what is y1 of -2.1, enter. And that gives me 21.5. Let's do this again, of -2.01. That gives me 201.5. And I'm going to expect for you to be able to see the pattern by now, but let's see it, 2001.5. Now notice that if we did -2.0001, it'd be it would be 20,001.5, and so on and so forth. Notice that as x gets closer and closer and closer to the number -2, this number is simply getting larger and larger. It's going up to infinity, basically. Alrighty, let's do this again. But this time, let's do it -1.9. And it starts out at negative 18.5. Do this again. Throw out another 9, gives us negative 198.5. Throw on another 9, negative 1,998.5. And if you throw on another 9, that's going to give us negative 19,998.5. So as x gets closer and closer and closer to the number 2 from the right-hand side, like we have here, this is getting smaller and smaller and smaller. In other words, it's going down towards negative infinity. And again, we could see that from the graph. So if I go ahead and draw a vertical line at x equaling 2, or close enough to 2. There we go. Notice that this is approaching positive infinity from the left-hand side and negative infinity from the right-hand side. And so there you go. Now, what this is telling me, though, is that this limit doesn't actually exist. From the left-hand side, the function is not approaching the same thing as it does from the right-hand side. Therefore, the limit does not exist. That's something very important to remember. So if the limit does not approach the same thing from both the left and the right, the limit simply does not exist. Alrighty, I'm going to go ahead and go back to the notes, and I will see you there. Okay, welcome back to the notes. So in the notes, we have a couple of things we've determined. We have the fact that the limit as x approaches negative 2 from the left-hand side of the function is going to go up to positive infinity. We also have the fact that the limit as x approaches negative 2 from the right-hand side of the function will be negative infinity. So notice that this is going up towards infinity, this is going down towards negative infinity. So this is going to infinity, this is going to negative infinity. Notice that these two things are not the same. The limit simply does not exist. Therefore, the limit as x approaches negative 2 of the function f of x does not exist. Now, the does not exist, you could limit that to just be DNE. That's the nice acronym for it. So the limit of as x approaches negative 2 of f of x is equal to does not exist. That works as well. Now, here's the thing. Even if both of these were infinity or both of these were negative infinity, technically that does not exist because infinity is not a real number. Infinity is just an idea. It's the largest number you can ever think of plus one more. So as a result, if you ever have infinity, technically it does not exist, period. But if both of them were equal to infinity, we actually do say that it would be equal to infinity. It's understood that the limit does not exist, but we're saying a little bit more than we would just by saying it does not exist. Or if it was equal to negative infinity, the same way. Alrighty. Well, I believe that's it for this video. I'm going to go ahead and end it here, and I will see you in the next one. Have fun.